Remember this number. You're going to need it later. Don't write it down. That's cheating. Just try to keep it in your mind. Try to remember it. Today we're going to talk about memory. Memory is actually a big umbrella term for a lot of systems with different properties. And those different systems operate on different types of information, sort of different modules for doing different things with different information on different timescales and with different capacities and different constraints. So there is a lot of variation here, but we're going to lump all of these things together under the umbrella term of memory because there's one thing that they all have in common. All of these systems, in one way or another, are about storing and retrieving information. I know I've said this before, but in a lot of ways, a computer is a lot like a human mind. In a lot of ways, a human mind is really just a kind of computer. And this is also true for memory systems. There is a very strong parallel between how our memory system works as humans and how the memory systems work in this machine. This is the computer's hard drive. This is where the computer stores all of its information. It's long-term storage. Just like we have long-term memory storage in our own minds, the computer has a place where it stores all of its information more or less permanently. And it does so on a disk, a magnetic disk. It has a way of physically encoding information on this disk where it can retrieve it later whenever it needs to. So just like a computer, we also have a kind of hard drive in our minds. We have a long-term memory storage system. If you see inside here next to those cooling towers, you may see the RAM sticks. Well, what's RAM? RAM is random access memory. This is the type of the memory that the computer uses to do basically anything. Any type of process or operation the computer needs to do, it does using its RAM sticks. Essentially, RAM gives the computer a place where it can temporarily store information. A buffer that can contain information while you need to do some kind of process, but a buffer that will be wiped clean when you turn the computer off and on again. This is a lot like our short-term memory or our working memory. We have a buffer where we store information when we need to do processes, just like the computer does. We have a sort of RAM that works for our own mind. How much RAM do we have? How big is our hard drive? Those are the questions that we want to answer as cognitive scientists. This computer served me very well over the years. I'm glad you could have one final function. There are several stages to the memory system. Our sensory memory has the job of intaking information. It takes information from our senses. It does some initial processing. It's largely unfiltered. It has a very high capacity, but it's very short-lived. It takes in all that information from our senses and records it faithfully and sends it on to the next memory system. So sensory memory is doing something important. It's performing a type of encoding. It's building representations of a particular type. And there are different sensory memories associated with different sensory modalities. Vision, audition, olfaction, smell, taste, touch, all of these things have their own kind of sensory memory attached to them. So our sensory memory systems are modular. They only deal with a specific kind of information, and they generate specific kinds of representations. After sensory memory, information gets passed on to working memory. The purpose of working memory is to access and manipulate information. It's where we perform all of our mental operations. There's some filtering that happens here. The unimportant information from our sensory memory is discarded. We only take the bits that we care about, and that's where we will work with them. So it has a limited capacity, but the information is retained as long as it's being used. And through rehearsal, if we rehearse the information that's in our working memory, items can enter long-term memory storage in a process called consolidation. Our long-term memory is for storing information for access later. It's for long-term, potentially indefinite storage. It's a kind of mental library or a mental database, and has a much higher capacity than working memory. So how much is actually in your long-term memory? We don't really know. I don't think we've ever successfully tested the full capacity of our working memory. It seems you can keep adding to it and adding to it and adding to it, and you'll still be able to retrieve no matter how much you add. It has a much longer duration than working memory or sensory memory because its purpose is to store information indefinitely, in some cases for your entire lifespan. And it's a much more stable form of memory. These memory systems have analogs in electronic computers. Our working memory is a lot like the RAM of a PC. RAM is what allows the computer to do all of the processes that it does. It's where it stores information temporarily as like a workspace. Same is true for our own working memory. And the hard drive of a PC is a lot like our own long-term memory. It's for long-term stable storage where information can be organized and then retrieved later. So sensory memory has a large capacity and a very short duration. Working memory has a small capacity and a short duration. And long-term memory has a large capacity and a large duration. Each of these memory systems differs in terms of its capacity and the duration over which it can hold information. Let's zoom in and focus on sensory information. All the information from your senses passes through your sensory memory before going to working memory and potentially, eventually, long-term memory. We have different modules associated with particular types of sensory information. So we have different unique types of sensory memory that are attached to different sensory modalities. All of them have a very short duration and a very large capacity. For some of them, the duration can be as short as 100 milliseconds, maybe only up to 300 milliseconds. That's only a third of a second. So that's true of our visual sensory memory, our iconic memory. When you open your eyes, your brain receives a high-quality image of the world around you. It's full of detail. But that image only lasts a fraction of a second, maybe only up to 300 milliseconds, up to a third of a second. So your brain has to decide very, very quickly which details it's going to keep, it's going to send on to working memory, and which it has to discard. It's too much information there really for your working memory to handle. It has to decide what information is important enough to send up the chain and what is going to get thrown away. We also have an auditory sensory memory, which we call echoic memory. It's like an echo. It's like the echo of what you've heard. So just like visual sensory memory, just like iconic memory, in echoic memory, everything you hear is faithfully transmitted to your auditory sensory memory. And it lasts a little bit longer than your iconic memory. It lasts maybe a couple seconds, something like 3 or 4 seconds. But it's also filtered before reaching your working memory. So what we hear is this cacophony of noise at all times, right? We're always hearing lots of noise. But only a small amount of that is actually getting transmitted faithfully into our working memories. Sensory memory also has the important job of encoding information. When information enters sensory memory, it has to be transformed into some kind of mental representation that our minds can actually utilize, something that makes sense to our minds. We talked about this before when we talked about mental representation. Information from the outside world has to be converted into some kind of format that our minds can use, something that's useful to our minds, before we can actually do anything with it. So this is a process that happens in our sensory memory. That's where the information from our senses gets encoded in a way that can be useful to all of the other systems operating in our minds. And the type of representation is unique for each type of sensory information. So our iconic memory might use mental images. It converts that information into imagery. Our auditory sensory memory, our echoic memory, will generate some kind of auditory representations. Our olfactory memory will generate some kind of smell representations. We'll have some kind of unique encoding for each different sensory modality. How do we know what the capacity and duration of these systems is? Well, let's try a little experiment. I'm going to flash a block of letters on the screen for a fraction of a second. It's only going to appear for a short fraction of a second. So you're not going to have a lot of time to study it. What I want to know is how much of that you can remember. So you're going to see this block of letters for a tiny fraction of a second, and you're just going to try to remember and recall as many of those letters as you can. Are you ready? Let's go. Just fixate on this cross, and then the letters will flash right on that space. All right, how many of those do you think you can recall? Maybe 3, maybe 4? You're probably not getting the entire block of letters. This is really hard. Okay, let's try the experiment again with a little modification. This time, we're going to do it again. We're going to show that block of letters for a fraction of a second. But we're going to follow the block of letters with a tone. So you're going to see that block of letters for a short fraction of a second, and then you're going to hear a tone. And it's either going to be a low tone, a medium tone, or a high tone. The idea here is that the tone you hear will determine which row of the block of letters I want you to remember. So if you hear that lowest tone, that means you have to try to remember the lowest row of letters. If you hear that middle tone, that means you have to try to remember the middle row of letters. And if you hear the high tone, that means you have to try to remember that highest row of letters. Make sense? So you're going to see that block of letters flashed on the screen for just a fraction of a second. Then you're going to hear a tone, and the tone is going to tell you which row of letters you need to remember. So you're only going to figure out what row it is after you've already seen the block of letters. It's not going to help you figure out what row you should focus on when you're looking. It's only going to help you figure out which one you're going to focus on when you're trying to remember. So I'll just play the tones again real quick. This is the low tone. That means that you're going to try to remember the lowest row of letters. The middle tone, the middle row of letters, and the high tone, the highest row of letters. Try to remember as much as you can. Okay, how'd you do? Was that maybe a little bit easier? Well, these studies were done in the early 60s, and what was found was that when we do whole report, when we try to remember the whole block of letters, all 16 of those letters, we can only remember a few items, maybe 3 or 4. It's very difficult. But when we're asked to recall a single row, we can often name all the items in that row. And we can do this for any given row without knowing ahead of time which one we're going to have to remember. Why is that important? Well, this tells us actually 2 very interesting things about sensory memory. It tells us, one, that sensory memory is full of detail. The fact that you can recall any of those rows without knowing ahead of time which one you're going to be asked means that all of that information is in your sensory memory. Your sensory memory has accurately and faithfully recorded all of that information, all of the letters and all of the rows of the whole block. So we're accurately recording that full scene, all of those letters. But the mental representation, right? The mental representation, the information in your sensory memory only lasts a fraction of a second. And that's why we can't report them all. So these results tell us, one, that sensory memory is full of detail. They also tell us that sensory memory has a very short duration. Because the reason that we can't report back all the letters, the reason we can't remember everything, it's not because we didn't see everything. It's not because all of those things aren't in our sensory memory. It's because our sensory memory fades so quickly that we don't actually have enough time to scan the entire image in our sensory memory before it disappears. We only have enough time to look at maybe 3 or 4 of those letters before the entire image dissipates and it's gone forever. That's why we can recall any one of those rows in full detail, because that's how we have enough time to look at a full row. We don't have enough time to look at all of the rows, but we have enough time to look at one of them. So when we use that cue, when we're given the cue, we can decide very quickly which letters we should send to working memory so that we'll still be able to recall them once that sensory echo dies. I think this is really fascinating, actually. It tells us that all of that information is in sensory memory, but we just don't have enough time to look at all of it. We have enough time to look at some of it if we know which parts we're supposed to be looking at. So that's sensory memory. Sensory memory, where our information goes from our senses. It's the first stopping point for information coming in from the outside world. Our sensory memory encodes all that information, but only a small amount of it actually gets sent on to the next stage of processing, to working memory. We can refer to this memory system as either short-term memory or working memory. I've seen it referred to both ways in a lot of literature, and there's a lot of debate back and forth about what the proper name for this memory system should be. I think both of these are fine for our purposes. I personally like the term working memory because I feel like it's really descriptive. It sort of encapsulates what this memory is for. It's for working. It is the workbench or the workspace of our minds. I think this is a good way of thinking about short-term memory. So it has a longer duration than our sensory memory, but it also has a much more limited storage capacity. Our working memory only holds small amounts of information for relatively brief amounts of time. So it is a longer duration than sensory memory. Sensory memory is very short-lived, but it is still relatively brief. If something goes into your working memory and we don't do anything with it, it will decay and leave our working memory within a minute or so. So this is where we're going to hold that information from our sensory memory. All the information that survives that attentional filter, that gets through our sensory memory, it goes into our working memory. But only a small amount of it can actually enter our working memory because our working memory is very limited. So this is what we're keeping in mind. It's like, you can think of it as sort of a mental scratch pad. It's like scratch paper. When you're taking an exam and you want to do some calculations. This is what your mind is doing too. Your mind has to have some kind of scratch space where it can doodle and make notes, do calculations. That's what our working memory is for. So our working memory is like the workbench of our mind. You can also think of it as kind of like the RAM of our minds, right? A PC has RAM. That's what the PC uses to do all of the computations that the PC does. If you want to build a really fancy gaming PC, you need a lot of RAM because running games with really good graphics is very intensive. It requires a lot of working memory. If you're doing calculations with very large data sets, then you need a lot of RAM. So the computer uses the RAM to do all of its processing, all of its computations. Same thing's going on in our own minds. We are using our working memory resources to perform all of the computations that our mind performs. Whenever we need to work with a piece of information to do anything really, that operation is going to occur in working memory, or at least some kind of working memory. We may have special partitioned working memory resources that are allocated for specific functions. Like maybe there is one just for language, and maybe there is one for vision, and maybe there is one for doing arithmetic. Maybe there's one for music. Maybe some of this is shared. This is something that's still being researched, the overlap between these different systems. Baddeley and Hitch in the 70s hypothesized that we had at least a few different kinds of working memory systems associated with different types of sensory information. They proposed a visual spatial sketchpad for visual information, where the information from our visual sensory memory, our iconic memory, that's where it will go. We'll go to our visuospatial sketchpad. And they proposed a phonological loop for auditory information. Things that go through our echoic memory will go to the phonological loop. And they refer to it as a loop because that is frequently what it's used for. It's used to repeat information in your head. You may even hear it in your inner voice as you repeat something like a phone number or a person's name that you just met. You might repeat it in your head so that you can remember it. You may recall from our timeline of cognitive science those pivotal events of the 20th century that led us to where we are now. You may remember George Miller in 1956 wrote a book called The Magical Number 7, ± 2. And that refers to the capacity of our working memories. George Miller was interested in what the capacity of our working memory actually was. He wanted to quantify it in certain terms. He wanted to be able to operationalize what the bits of information actually were in our working memory and how much it could actually hold. What he found is that our short-term or our working memory seems to have a capacity of about 7 items. So if I give you a series of random letters As long as it's within that range of somewhere between 5 and 9 maybe, you should be able to remember it. And maybe you'll remember by repeating it to yourself, or maybe you'll just remember the way it looks. But that should be about the right number of items that you can keep in your working memory, sort of indefinitely. But of course, this raises the question of what counts as an item? If my working memory can hold 7 items, it's kind of important and meaningful to talk about what an item is. What counts as an item? Well, it turns out that what counts as an item can vary. Maybe one letter counts as an item or one number. But we can also chunk letters or numbers together into larger units. And then those become the new items. So if I give you a random string of 12 letters, that's quite a bit to remember. It's quite a bit to keep in your working memory. It's more than 7 plus or minus 2. So it's a bit of a challenge to keep all of that in your working memory and keep it refreshed. 12 items is a little bit heavy. But what if we can take those 12 items and group them into familiar units? So maybe I don't give you 12 random letters. Maybe I give you 12 letters that form familiar acronyms like NFL, CIA, FBI, MTV. These are probably all acronyms that you're at least somewhat familiar with. You've probably heard them before. So if you see this list of apparently random letters, if you recognize the acronyms contained in them, it gives you a shortcut. You can use those as the items. And now, instead of there being 12 items, there are only 4. Suddenly, this becomes a lot easier to keep in your working memory. Even though it's the same number of items in the sense of it being the same number of letters as that previous list of 12 letters. Suddenly, this becomes a lot easier because it's only 4 chunks. Those chunks becoming the new items. This is actually one of the secrets of super memorizers. These people are really, really good at memorizing stuff. They seem to have like impossibly good memories. Well, they use a bag of tricks. Really, anyone can become a super memorizer. It's not like a genetic thing. Anybody can do it. You just have to learn the bag of tricks. And one of the tricks in their bag of tricks is very efficient ways of chunking information. People who are super memorizers have become very good at creating chunks, consolidating the information in their working memory into recognizable units to reduce the total number of items. This process of reorganizing or modifying information in our short-term memories is actually called recoding. So our sensory memory encodes the information. We take it in through our senses and we encode it into a representation. Then it goes into our working memory, and in our working memory, we can recode it. We are not tied down to that representational choice forever. We can take that representation, take that information, and we can rearrange it and maybe organize it in a way that's better for our working memory, that reduces our working memory load. We refer to those bits, the meaningful units of information, as information bits, taking after Claude Shannon. So things like letters and numbers and maybe even words we can think of as being bits in our working memory. They occupy the atomic space. They are sort of atomic units of memory. And we can take those bits, we can group them into larger chunks. We can refer to those as just information chunks. Of course, those information chunks become sort of the new items in working memory. They're sort of like taking many bits, combining them into a single chunk, and then that chunk becomes the new bit. Sort of a recursive process that lets us organize information in our working memory in a very efficient way. Our sensory and working memories are both subject to decay. Items leave the workspace over time. Obviously, this happens a lot faster in sensory memory, like for iconic memory, the visual sensory memory. Items will leave that space in under a second. It's very, very fast decay. In working memory, the decay is a bit slower. When things go into working memory, they might stay for a minute or two before they sort of evaporate. But the decay is still present. Everything, once it goes in, things immediately start to decay. The memory starts to fade. Of course, you can delay the effects of decay by repeating things to yourself. That's one way that we can keep the decay at arm's length. By talking to yourself, using your phonological loop to repeat information using your sort of inner voice. Right, so this type of repetition, it's going to vary by modality. Your phonological loop will have some kind of inner voice, but your visual spatial sketchpad might just consist of you looking at an image or redrawing it in your mind. So what this does is it refreshes the items in your working memory and it prevents decay. It keeps things fresh, keeps things from leaving your working memory. And this process of just repeating information to yourself, we call maintenance rehearsal. It's just maintaining things in your working memory. If you do this long enough, maybe it will go to your long-term memory, but it's not the most effective or efficient method of consolidating information into your long-term memory. Elaborative rehearsal is a much more effective way of consolidating information from your working memory into your long-term memory. And what elaborative rehearsal does is it links new information that has just come into your working memory, with existing memories, existing information that's already stored in your long-term memory. So you're creating links between old information and new information. And that turns out to be a really good way to transfer information from short-term memory into long-term memory. So I know that flashcards are pretty popular as like a study aid, but there are a lot of research that shows that it's not the most effective choice. Repeating information is just not the most effective way to store it in your long-term memory. It's much more effective to build connections between what we already know and what we are learning. So maybe this is like a study life pro tip for our study habits. Instead of just repeating information to ourselves, it really helps us to take new information and link it to old information. Do you remember that number that I asked you to remember at the beginning of lecture? You may have completely forgotten all about that. But when I asked you to remember that number, how did you choose to remember it? What strategy did you use? Did you repeat it to yourself in your phonological loop? Did you keep it refreshed in your visuospatial sketchpad? There probably wasn't a way for you to perform elaborative rehearsal because it doesn't really link to anything you already know. It's just a random number. So I think our typical strategy for something like this is going to wind up being some kind of maintenance rehearsal. And then you have to sort of hope that maybe it gets into your long-term memory. There's no way that you've been doing maintenance rehearsal this whole time. You really can't and pay attention to what I'm saying at the same time. We only have so much working memory to deal with, and we need it for both of those tasks. So don't feel bad if you didn't remember that number. I was kind of setting you up a little bit. I know that if our positions were reversed, there is no way that I would remember that number by now. It would be gone. Totally evaporated into the ether. So that's expected. It's expected. Maintenance rehearsal is not a very effective way of remembering things for a very long time, especially if it's something that doesn't have any context and doesn't mean anything to you. An interesting consequence of the fact that our working memory has a very finite capacity and the fact that it has decay is something called the serial position effect. So suppose I were to show you a list of random words, and then at the end of that I ask you to recall as many of them as you can. If we were to chart our accuracy in this task, what we would see is that we are much more accurate for words at the end of the list, the last words that you heard. And you're going to be more accurate for words at the very beginning of the list. And our lowest accuracy is going to be in the middle, the words that were in the middle of the list. So why is that? How can we explain that based on these very simple properties that we know to be true about working memory? Well, think of it this way. When we ask you to do this kind of memory task, we give you a list of words and we say you're going to have to remember these. The most likely strategy that we use is going to be maintenance rehearsal. We're going to be repeating those words in our phonological loop. And the longer we repeat them, the more likely it is that they will enter into long-term memory. So for the words at the beginning of the list, those words come into an empty memory buffer. Your working memory is effectively empty when you start this task. You're not currently rehearsing anything, I hope, when you begin a task like this. You should be really fresh and think, okay, I'm ready. My memory buffer is open. Let's go. First word goes into the memory buffer and we start rehearsing it. Then the second word's in. Oh, now we're rehearsing that word. The third word, the fourth word. At some point, our memory buffer is going to fill up. Once it fills up, we have a choice to make. We have to think, okay, do I want to keep rehearsing what's already here? Or am I going to jettison some of this to make room for the new stuff that's coming in? And it's going to keep coming and keep coming. So that first word that goes into your memory buffer, you actually have the longest time to rehearse it because it's the first thing that comes in. It comes into a completely empty buffer. And as more things come in, the buffer is filling up, and the rehearsal gets less effective. So that's why we have relatively good recall of the very first few words, because they're going into a relatively empty memory buffer. They get a lot of rehearsal, a lot more than the words that follow. Well, what about the words at the end? Actually, our highest recall is for the words at the very end of the list. What's the story there? They're not getting that much rehearsal time. They're coming into a full buffer, and it's happening at the very end of the experiment, so it's not like you get a lot of extra time or anything. Well, your recall of those words at the end of the list is really good because when you actually sit down to recall all of the words, those are the words that are still in your working memory. So you get to like a near 100% recall for like the very last word of a list in a task like this. Why? Because it's still in your working memory. It's still really accessible. It's still fresh. Whereas the word at the beginning of the list, you just have to hope that you've rehearsed it long enough that it has made its way into long-term memory. That's really the only hope for remembering the word at the very beginning of the list. There's no way it's stayed in your working memory this whole time. So yeah, the most reliable memory that we have is going to be if it's still in your working memory at the time when you have to remember everything. Our second most reliable memory might be the thing that we rehearsed the longest and made it to our long-term memory. The stuff in the middle, well, it's probably not in your working memory and it's probably not in your long-term memory either, so our accuracy goes way down. That's what gives us this serial position effect. We also sometimes refer to this as primacy and recency. Primacy, the first things in the list get remembered really well, and recency, the most recent things you saw on the list get remembered really well. So let's just review sensory and working memory, how these systems interact with each other. Information comes in through our senses. Our sensory memory takes in all of it. We get a very faithful rendition of all this information that's coming in through our senses. That's a lot of information. It's really too much for our minds to handle. And so we have a very strong selectional filter. Only a small amount of that information actually moves on into working memory. And what's in our sensory memory, it's very high capacity, but it's very, very short-lived. So it's a very short amount of time that your brain is trying to decide what information it's going to keep and what information it's going to discard. So that small subset of that information goes into our working memory, and in our working memory, that's where we can refresh it and we can work with it. We can do all of the operations that our minds normally do with information. So this is where we're going to build a sentence. This is where we're going to analyze a scene. This is where we're going to imagine things in our mind's eye, do those scanning, mental rotation, zooming. All of those operations are occurring in our working memory. If we work with something enough in our working memory, if we rehearse it enough, if we elaborate it and link it to things in our long-term memory, then it will undergo the process of consolidation. It will move into our long-term memory. So information from our working memory that's been rehearsed enters long-term storage where we can retrieve it later. And then once it's in our long-term memory, then at some later date, we can retrieve it. We can go back and we can get it. We can pull it out of long-term memory. We can send it back to working memory and we can do new things with it. And this is something that's happening all the time. We're always using old information and new information and synthesizing it. It's all going on in working memory. And it's all at the intersection between sensory memory, working memory, and long-term memory. So let's sum up the key concepts from this lecture. We talked about sensory memory with its large capacity, short duration, where we perform encoding. We talked about short-term or working memory, which has a small capacity and a short duration. This is where we perform maintenance and elaborative rehearsal. We do all of the operations that we need to do with the information that goes into our working memory that we might want to go into our long-term memory. We perform chunking. We can take bits of information, we can group them into meaningful units. This is a more efficient way of organizing information so that it doesn't require quite so much working memory. And of course, items in working memory will decay over time. That's why we have to keep them refreshed by doing maintenance or elaborative rehearsal. And we talked a little bit about long-term memory, which has a very large capacity and a long duration. In the next two lectures, we'll talk more about memory. We'll talk specifically about certain operations that can happen within memory. We'll talk about memory search and how we can use the tools in cognitive science to figure out exactly how an operation or a process like that works, which I think is super exciting and cool. And then we'll talk about the long-term memory systems in more detail. Once we take things from working memory into long-term memory, well, what happens then? What are all of the long-term memory systems? How do we store and organize information? How do we retrieve information? Turns out that it's a very active process and there's a lot going on there. So there's a lot to talk about.